Hello. This is a very brief introduction to the library pca3dvis, which you can see at github.com/tjstretchalot/pca3dvis. This is going through the examples all random, and what we're essentially going to try to do is plot some random three-dimensional data, and we're going to see the output that we get from pca3dvis. And we're going to try to plot some five-dimensional data, which we're going to project down into 3 dimensions and see that we can do that very easily. So let's get started. So the first thing we're going to do is we're going to have to generate some random data. So let's just use uniform random data. So let's say we want to look at some, we have 1,000 samples that were randomly generated from a three-dimensional cube with side lengths 2. So they go from points go from -1 to 1. So here we are. We have some random data. Now we're just going to plot exactly that data. So we're going to use a projection matrix that's just the I. So and that's the identity here. So we have a projection matrix that takes our already three-dimensional data and just maps it to itself. And we're going to have we're going to label every point the same. So we're just going to give every point a label of 0. So we have 1,000 samples. So 1,000 samples, and for it doesn't actually matter, but we'll just give our labels in int32 data type. So we have some 0 labels. So now that we've kind of described our data, we have some random dimensional data. We've decided a projection matrix, which is just going to be the identity map. And we have some labels. In this case, everything is labeled as 0. We need to decide how we're going to style our scatter plot. And how that works is we're going to create a little list. Here we only have one matrix, so we're going to have to describe a style. We're going to have to describe a style that applies to every single element. So we're going to style everything the same. So we're going to say label as shape. Another way you can think about this is label equals 0. So for everywhere in the data where the label is 0, which is everything, we're going to style it the size of the point. We're going to give it 20, and we're going to color it tableau red. Fantastic. So what we've decided to describe here is how we're going to style each point. Okay, so now we're ready. Now we have everything. We've decided a style for every point. So we've decided everything with a label of 0. We're going to style size 20 and the color red. And the other attributes will be the default styling attributes of matplotlib scatter. Now we're going to actually introduce the pca3dvis library. So snapshot and trajectory and the worker. So the snapshot is the single data, the trajectory is a sequence of data, which in this case is a sequence of a single thing, and the worker is the thing that actually produces videos. So we need to create a snapshot. So a snapshot is just the actual data combined with the labels projected with a particular projection matrix. So project with matrix, the data, our labels, and the projection matrix, which we recall is just the identity map. We also want a trajectory, which is a projected trajectory, which is going to accept a list of snapshots, which in this case is we only want a single snapshot. And finally, we want to actually produce the video. So let's go ahead and do that. So we pass it the trajectory that we want it to make a video of. the markers that we want, a title for each of the snapshots. So we only have one snapshot, so we have a list of a single title, and where we want it to save. So let's call it just save to out. This is going to take a moment. So you can see here it's decided that it's going to take 12 seconds on this video, and this is running on a computer with 12 cores, 12 physical cores, so it's decided to use 4 workers. Now these are some kind of generic settings that might not be optimal for the particular the computer that you're using. So over time it typically starts to generate images a little bit faster. So here it's already spawned an additional worker, but either way it's not going to take too long for it to generate a video of a single set of data. And we finished. So now we can just look at our data. So you'll see it's produced some snapshots. So if we wanted to look at a particular snapshot, this would say this is the layer and this is the rotation. So a rotation of 45 is pretty standard. So let's try looking at that. That does indeed look like some random data. You can see it's a very big image. And we can look at the snapshot, the video. And there you go. So I'm recording this in a fairly low frame rate, but if you were to look at this, this is 60 frames per second, 1920 by 1080, as it promises. And it would do a full rotation. And you can see the library for an example output for an even longer video. Next, I want to quickly show you how you can create a trajectory from higher dimensional data. That's actually easier than when we are trying to create we're specifying the projection matrix ourselves. So if we had some higher dimensional data, so R2 maybe, which is also random data in a hypercube, but now instead of it being in 3 dimensions, say it was in 7 dimensions. To create a trajectory from that, all we have to do is import, so I'm going to use principal component analysis here. So that's a technique for lowering the dimension of data that's provided with this library. So PCs. The second trajectory here we can generate with just pca3dvis.pcs.get PC trajectory. We pass it the label, we pass it the data that we want to project down into a trajectory, and this is going to be passed as a list of arrays. Now each array that we pass it has to have the same number of samples, but it can have a different number of features, and it will turn into, each one of them will turn into a snapshot, which will go into the trajectory. So here we're going to get a trajectory with a single snapshot because we're passing in a single array. And then we need the labels as well. So we're going to use the same label since we also chose doesn't. And just like that, we have another trajectory. And if we look at it, it has a single snapshot. And if we wanted to plot it, we could plot it in the same way. We just change trajectory to trajectory 2. So that's everything I wanted to show today, and I hope this shows you that this is a very easy library to use. It works in just generic 3-dimensional data, or you can pass it higher dimensional data, and it will just very easily project it down into 3 dimensions, and you can look at that, and whatever information you can get out of principal component analysis, you can get out of this in 3 dimensions.